Okay, so hi there folks. We're going to continue our video from the last one. We're going to answer this example written here. Again, let me read this. Consider the experiment of tossing two fair coins and define the events. So we have A, wherein two heads come up, B, where two tails come up, and we'll be determining the A intersection B. That's for number one. For number two, we are going to determine A intersection B quantity complement, and we're going to determine in number three A complement union B complement. So have a copy of this, and I'm going to hide this in a while, and we're going to show the spreadsheet, or rather the um the uh the paper, the whiteboard, so that we can answer this. Okay, so have a copy of this, and let me put this aside, and we're going to answer this. So we're going to consider an experiment of tossing two fair coins. So imagine if we're going to toss two fair coins, it's going to be something like this. So we're going to have heads first. These are all for the first toss. Okay, wherein we have two possible outcomes. It's either going to be a heads or a tail. So those are the only two outcomes, right? And then we're going to consider the second toss, wherein we're going to extend here in the heads. It can be that in the after the first toss and you got a head, you can still get a head or a tail in the second toss. And if you got a tail on the first toss, you can have a head or likewise a tail again. So this is where um, the second toss is found. Okay, so this is our second toss here. So let us define this. This is the first toss. This is the second toss. And let's put that and write that in a set notation, that is in listing method, in so that we can define the sample space. So we will call S as our sample space, big S, and we will call these as our outcome. So we have HH here. So H and H, that's two heads, meaning you got two heads in the two tosses. You may have HT, head tail. In the first toss you got the head, and on the second toss you got a tail. Next is we can also get a tail in the first toss but a head in the second toss. So what we have is TH, tail head, that is. Or we can also get two tails for for the two tosses. That can be TT. Okay, and those are all the list of our sample spaces. And we will call event A, we will denote event A to be two heads come up. So there's only one outcome where two heads come up. This is the outcome here. So we're going to call event A to be, well, it's a simpleton, a set that only has one outcome or one element. So that's our event A over here. And we will call our event B to be an outcome wherein two tails come up. So if we're going to strictly find an outcome wherein strictly two tails come up, we only have TT here. So what we have is T, T, that is tail, tail. Okay, so those are our two predetermined events. What we need to do is to find the values or the outcomes or the set of elements of these numbers. So we're going to first consider for number one, we're going to consider a intersection B. So A intersection B. So what's the intersection that is the common outcomes of events A and B? So we can see that by inspection that there are no common outcomes between A and B, because A is strictly all heads, B is strictly all tails. So there's no common outcomes. Therefore, we say that their intersection is a null set. Okay, their intersection is empty. Okay, now how about for number two? We're tasked to find um, A intersection B quantity complement. So that is, we're going to get the complement of this null set here, of this empty set here. So based on our number theory, or sorry, our set theory rather, when we have the complement of a null set, that will be equal to your universal set. Okay, the complement of a null set is equal to your universal set. Our universal set in this scenario, in this context, is going to be the sample space itself. Hence, A intersection B complement, well, the null set, the complement of a null set is the sample space. Therefore, A intersection B will be equal to HH, two heads come up. We can also have the head on the first um, toss and tail on the second toss. We can also have a tail on the first toss and a head on the second toss. And then, you know what? Tail on the first toss and a head on the second toss. And lastly, we can also have two tails at the same time. Tail on the first toss and tail on the second toss. Okay, so that is our answer for number 2. So again, notice that this is just equal to the sample space. Please excuse my penmanship over here. Now, for the number 3, we are tasked to find A complement union B complement. Okay, A complement union B complement. Now, what is that? Okay, now A complement, let's list that first. Okay, what is A complement? A is the two heads. So what are the other elements in the sample space except these two heads? So that is going to be HT, TH, and TT. So let me write it down. So what we have is HT, then we have TH, we also have TT, and those are the elements in our A complement. Now we're going to get the union of that with the B complement. So the B complement, the B itself is double T, two tails. We're going to get the complement of B, so that's going to be all the outcomes in the sample space except this double T. So what we have is HH, what we have is HH here. Then we have HT. Then we have TH. And there we go. Those are the elements of B complement. Okay, so what we're going to do is we're going to get the union of this sets here, the A complement and the B complement. And we don't need, remember, a definition of a set is that it has a well-defined um, collection of objects. So when you say well-defined, there should be no repetition whenever we are writing. So we're going to continue here since we cannot fit it. So what we want to do is we're going to combine this. Okay, so we have first the HH. Then we only need to write the HT once because we have an HT here. We also have an HT here. We need to only write that once. So we have HT over here. And we also need to write TH once, TH here. So therefore TH. And we write the TT also, which is double-tailed. Uh, okay, so what we want to see here is that clearly this A complement union B complement is just equal to your sample space. Okay, now notice here that number 2 is equal to the sample space. Number 3, A complement union B complement, is also equal to the sample space. So therefore, hence, we can say that number 2 here, this quantity A intersection B complement is equal to A complement union B complement. And this actually are two important, these are important equivalences in logic. We call this the De Morgan's laws. So let's define that these are one of the laws. Actually, we have two laws for De Morgan's, from the mathematician Augustus De Morgan. That is where the name came from. Um, De Morgan's laws. Actually, it's laws because there's two of them, which is very much important in logical equivalences topic in logic. So writing number two over here, number two is intersection B quantity complement. So let's write it down. Um, A intersection B, A intersection B complement is, we say it's equal, or actually it should be equivalent. These are the three parallel lines to A complement union B complement. So that is one of the De Morgan's laws. The other one is the opposite of it. Notice the connectors or the operations. So one of the other law is actually just very similar. A union B quantity complement is just logically equivalent to A complement intersection B complement. And these are what we call the De Morgan's laws. Okay? So what the first the one of the laws is written above. Okay, so this follows from our example here, from the um from the slides. Okay, we started here. We presented it and shown the sample space. We have events A and B. We answered 1, 2, 3, and it follows that 2 and 3 are actually taken from De Morgan's laws. Okay, which is actually stated here in our PowerPoint that this follows. Okay, the De Morgan's laws follows here for number 2 and number 3. Okay, so that is one of some special cases when we look at equivalences in sets. And actually, that's the end of our chapter 0, for the first part of chapter 0, that is, and sample spaces and events, that the definitions, the basics, and such. Okay, in the next lesson, we're going to talk about how to count sample spaces, how to count sample out points or sample outcomes from a sample space, and then we're going to apply the concept of probability theory right after that. Okay, so hopefully you'd like and subscribe. Keep updated. Please do hit the subscribe button so that you will get updated of the latest content. Okay. For sure, I'm going to create more of these videos in statistics and probability for grade 11. So thank you very much.